class. So, this should be fairly interactive, please, because it is a small group. Please feel free to ask questions. I will try to field those as we go through things as best as I can. So before we get started in the slides, let me share the notebook we're going to be using. So this is hosted on a GitHub page that I have. So it will be this, oops, not that one. It'll be this page. So I'll go ahead and post this into our chat. And if you're new to Colab or new to GitHub, you don't actually need to know much about GitHub for this class, but you'll just open up a page like this, and then you should be able to, there should be a button here that says Open in Colab. If you don't see that, let me know, and we can talk about that in the chat to try to figure out what's going on there. But you should be able to open this directly into Colab. All Colab requires is a Google account. So I believe you have to have some form of, some ID that is attached to a Google account to be able to open this and run this. Once we get into this actual notebook, I'll talk a little bit about how Colab works for anyone not familiar. So if you're not able to open this URL, please drop a note in the chat so that I can walk you through how we might be able to diagnose that. In the meantime, let me get started with some slides here, and we can just talk through what we're going to do today. All right, so for those of you not familiar with my work, my name is Derek Schultz. I am a designer and an artist, and I have for about the past year and a half been doing most of my work in machine learning. So that could be something like StyleGAN, which we'll be working through today, other various models that generate images. So I just recently finished up a project for the New York Times, doing some really great artwork and animations and other things that were a lot of fun. I tend to do a lot of editorial illustrations. So I work with magazines and newspapers and other editorial teams to generate art. So in the case of what you see here is, this is some classes I've been teaching recently, and sort of the impetus for this workshop, some style transfer work, which is done in the middle, and then a GAN, which we'll talk about in just a minute, obviously, and then some image-to-image translation. This is using a model called Munit, which is also from NVIDIA. So I sort of do the gamut of different things. StyleGAN being probably one of the more popular things that people are making with right now. So we'll talk about why that is and how it all works in just a moment. And yeah, so we're going to look at StyleGAN2. Actually, about 3 weeks ago now, NVIDIA, the folks who make StyleGAN, released a brand new version of it. And we'll talk about what the brand new version does and how it differs from previous versions. But the idea here is that hopefully after the end of this workshop, you might not be able to create this exact image, but you'll be able to do something like this, which is generating a model that interpolates. So we'll look at some pre-trained models that exist on the internet that we can work with, and we'll look at how to generate static images from a model and then how to also generate video. So with that, I will go ahead and jump into what is a GAN. So many of you may already know how GANs work and that sort of thing, but if you don't, I just want to give a very high-level overview of how a GAN works and what it is. And we won't really be dealing with training in this workshop. I've got some links if you're interested in understanding training, but GANs are really the powerful part is in how they train and how they're able to generate images because of that training method. GAN stands for Generative Adversarial Network. Generative meaning it produces images, so rather than a model that can classify this as a cat or a dog, it generates new images based on the training data. And adversarial we will talk about now. So the reason it's called adversarial is there are actually two different machine learning models inside of every GAN. One is called the generator, that is the one that produces images, and one is called the discriminator. That is the one that determines whether an image is real or not. And essentially these two models play a game, an adversarial game of trying to one-up each other. So the generator produces an image that it believes is real, and the discriminator either determines this is a real image, in which case the generator learns from that, or it says no, this is fake, in which case the generator tries to determine why it might be determined as fake. And over a process of going over and over and over and over again, you get better images. So once again, the discriminator says yes, is real, or no, it's fake, and then the generator goes, okay, well now I've got a new image that I think is even better than my previous fake. Try this one. And over this game, over days, weeks, months, in some cases, the generator gets better and better and better, and at some point we have a generator that can now produce realistic or semi-realistic looking images. The common sort of way you think about this, or the common analogy that people provide, is a forger and a banker. So the forger is trying to produce a piece of money that looks like it can be fooled by the banker will be fooled by. So the way a lot of these generators start is they start with like pretty bad or pretty low versions, low quality versions of what they're trying to generate. And the truth is the discriminator is also like not that smart. They both start out pretty unintelligent, and the discriminator, every time it gets faked out, the discriminator is told like, hey, that was a fake, you should really do a better job and learn why. And then they're able to get better. The generator then realizes that it needs to step up its game. It starts producing better images. And over this sort of cyclical process, what you get out of it are better and better images. And the truth is, I would say, like, if you were to really look at the details for most images, you would probably be able to figure out what the fake is versus what the real is. We're almost at pure realism, but not really there yet. Depends on the data set. But it gets to a place where it's pretty interesting and it's pretty easy to imagine, this thing being a real object or whatever it is. So this is the process of GANs. The GANs were actually invented in 2014, so they've really only existed in 6 years. And over that period of time, they started out very, very small. They were, I think, something like 28 by 28 pixels size, and black and white. And then in 2015, we were able to do color. But you'll notice this image is not that great, and it's probably 64 by 64. Then we got to maybe 128 by 128. 256 by 256, and now we're at 1024 by 1024, actually a little bit larger even if you do some customization. You can get pretty high resolution and pretty high quality. So in 6 years, due to both machines getting better, but also these networks getting better, we've been able to produce some really, really fantastic imagery. So that is a very, very quick introduction to the history of GANs. I think at about 2017 is when NVIDIA entered the fray. NVIDIA released a model called progressive growing of GANs. And what they were able to solve is there was a big challenge for a while of getting low resolution to high resolution. And NVIDIA was able to figure out sort of like how to do the leap from 256, which is nice, but not really useful for artwork, to 1024 by 1024. And that was sort of what was called ProGAN. GAN at that time was the precursor to StyleGAN. And when StyleGAN came out, so on the left here, what you'll see, if you're into machine learning and you know what these mean, that's great. If you have never seen a model or a graph like this, I'll quickly explain sort of how it works. But on the left here is what was a traditional GAN. The idea just being that at every convolution layer, so starting at 4 by 4 pixels to 8 by 8 pixels, 16 by 16, 32, all the way up to 1024, you have a certain like layer of processes. So you like upscale that, then you run your convolutions on it again, you upscale it again, upscale it again, upscale it again. This was essentially what ProGAN did. It was able to sort of figure out how to make the resolution larger as it went through each step, which was pretty powerful. When StyleGAN came about, what they introduced was this mapping network. And we'll talk a little bit about this mapping network as we go through generating some images. But the mapping network is able to improve the quality in a way they previously couldn't. So it's almost like you're taking on the right-hand side here what is like a traditional GAN, and then introducing this mapping network that is able to create better styles and better textures. And that was really, really key to generating really great imagery. This was, I believe, StyleGAN1. StyleGAN2 came about and made some new additions, basically figuring out what these actual convolution layers and what these other layers should be in order to work with a wider range of data sets, but also to be able to how do I want to describe this? Remove a lot of artifacts and things that were happening because of this network. So I actually changed out the A to N layers to produce new layers using a different technique, and they were able to get even better quality. And then 3 weeks ago, they released a new version, which is called StyleGAN2 ADA. And StyleGAN2, let me make sure. That's not actually the right slide. That's fine. This is what StyleGAN2 does. And what StyleGAN2 did is it switched out these ADA-in networks for some new architectures using some demodulation and some other techniques. We won't get into that too much in this course. If you're interested, you can always drop a note for me, and I'm happy to discuss a little bit more about that. We're mostly going to focus on being able to generate images and those sort of things from this. So this is StyleGAN2. They were basically able to swap out some layers to get better quality images. The latest version, which is StyleGAN2 ADA, doesn't really change the generator or the discriminator layers. What it introduced was a new technique for creating better training using augmentations. And I apparently don't have a slide for that, but the augmentations, what they did is during training, if you've worked with ever at all with discriminators or object detectors, you know that there's a lot of augmentations they do. That being like flipping, rotating, changing colors of things in order for the discriminator to become smarter and able to recognize a cat hiding behind something, or recognizing a cat that's upside down, those sort of techniques. So they're able to finally apply those to the StyleGAN architecture. And the real key there was that they were able to apply it in a way that was differentiable. So basically, the problem is if you were to augment your data set in training with flipping images upside down, the generator will learn to flip images upside down, and then you will get unrealistic images. So what happens is during training, they apply these augmentations, and then they are basically reversed as the generator begins to generate images. So it makes the generator and the discriminator smarter, and it produces higher quality images, but the augmentations don't actually affect the generator. If you hear anyone refer to leakage, leakage is the concept of these augmentations leaking into the generator, which they have been able to eliminate for the most part. I've run into some of it, but it's generally pretty avoidable. So that's a really, really quick, that's like what a 10-minute introduction to StyleGAN. That's pretty high level. I'm happy to provide links to the papers if anyone's interested in those, because there is lots of great detail in all of them. What we're going to focus on mostly is how to make images. Yeah, so if you're interested, this is the output. These slides are linked to from that notebook. If you want to dig into these a little bit later or leave comments or anything, you can do that. This is the layer network for the discriminator, and this is the layer network for the generator. So you can see sort of how each of these layers works. What we're going to focus on mostly for this class is talking about the latent space. So StyleGAN's output at the very end of a generator is, or actually I guess sort of its input. Its input is a 512 by 512 dimensional latent space. So what does that mean? So that means that in a space that looks like this. So imagine 512 dimensions squished down to 2, and you have a latent space. So at any point in this latent space is an image. So let's say at this point in this space, you see this image of a face. And if you move to a different space, you will see a different image. So the idea here is that images that are close to each other, right? So we pick these two spaces. If they're really close to each other in this space, they should look very similar. And the further apart they are, the more different they should look. So we're basically going to use that concept to generate our own random sampling of images, our own videos, and we're going to do some other funky things as we get through this example. So we're going to have a lot of fun. The thing to recognize is like this latent space is, it is, if you imagine it in 2 dimensions, that works, but it's really 512 dimensions. And that's really hard for our human brains to wrap our heads around, because we can basically only think in maybe 3 or 4 dimensions at most. But this is 512 dimensions of that space. And that 512 dimensions is a vector from -1 to 1. So it can be negative or positive, and it's a floating value somewhere between -1 and 1. And that's basically a mathematic value that we can then use to generate images from there. Any questions before I jump to the notebook? I will take silence as we're good to move on. Okay, so let me, so first off, everyone should have the notebook open by now. If you don't, please drop a note either in chat or speak up and we can help you get set up. So for anyone interested in Colab, if you haven't used Colab before, Colab is Google's version of Python notebooks. Here, I can go ahead and add this link into the chat for people. There you go. So should have that now. What is a Python, or what is a notebook? So notebooks are pretty common in data science. They're very commonly used as a way to sort of interactively work with the various pieces of data. They're more commonly known as Jupyter notebooks. That's sort of the most common version people use. And Google has sort of made their own version of it that allows you to work off Google GPUs. And what's really great about this is that the GPUs that Google makes available to us for free, sometimes run about $3,000, $4,000, $5,000, and we can just use them for free. Now we can't use them for free like every hour of the day. We have about a 20-hour limit at a time, in which case they will then restart the machine and we'll have to restart it from here. But for stuff like this, where we're going to spend maybe an hour using it, it's a really, really valuable opportunity to sort of use some really expensive and high-powered machines. I'm using a version of Colab called Colab Pro. It is $10 a month, and that's only available in the US or in Canada. So for many people, if you're outside the US or Canada, you're stuck with the free version, which is still pretty good, but it has some limitations. It has you will often have access to lower powered GPUs, and you have a shorter time limit. I think you have 8 to 10 hours to use. So just be aware that, like, what we'll be doing in this session will totally work fine for Colab. But other folks, if you try to get into some of the training materials or other things that I have linked at the bottom of this, you may run into issues. So just be aware of that. So a really quick exploration of the interface is along the left-hand side here are a couple key things. So first off is table contents. So this is going to show you all of the different pieces that are available in the notebook. You can jump around if you want to, or you can sort of like follow along with me. Notebooks are divided into cells, and those cells are text cells, which is a text, literally text you can read, and then a coding cell. So this works almost like Bash. It's a little confusing because it's not like a Bash cell exactly, but it is pretty close to a Bash cell. So this will allow us to run code directly in line and then be able to access that from our server. So it can get a little confusing depending on what you're doing. The way I've set up this notebook is it should be pretty self-explanatory in terms of the text and what you can edit. And then you'll just be running lines one at a time. And the way to run a code cell is you've got two options. You can either come over here and click the play button, or you can click into the cell itself and hit Shift Return. Both those run the cell. And there's no right or wrong reason. Just do whichever one you feel most comfortable with. So if you're following along, what I would love for you to do is, first off, make sure that at the top right of the page here, that you might have a button here that says Connect. Make sure that you click Connect. Once you are connected, go ahead and click in this very first cell and hit Shift Return. And you should get something that looks like this. Now, what this says, the line really that's really important to look at is this one here. This tells you what kind of machine you have available to you. I have a V100 that's very likely because I'm a Colab Pro. Some of you may have a P100 or a K80 or a T4. All of those will work for this class. In the future, you may want to be concerned about what you get here because that can affect speed of generating images. It can affect training times. It can affect a bunch of other things. So usually the first thing you'll see at the top of one of my notebooks is something that is this line, which just basically generates what the what version or what machine you're using and what machine you have available to you. So if you have a V100, a P100, a T4, or a K80, all of those are totally fine to work with. And you should be able to continue on with this workshop. I don't think you should run into any issues. If you're seeing something that isn't one of those, the last thing I would check is just make sure that you go to Runtime and then go to File, go to Runtime, change Runtime Type. Make sure this is set to GPU. If it's set to none, that might be your issue, and we won't be using TPUs for this workshop. So just make sure this is set to GPU, and then hit Save, and it might ask you to reconnect. Once you're there, that should be pretty much set up, and then you'll run this cell. So what I've done for this intro, just to sort of walk through things rather quickly, is I've sort of pre-run every cell in this notebook, which means we won't necessarily be waiting for things to generate or load. Generating images and generating videos especially will take some time. It can take 5 to 10 minutes depending on what sort of GPU you're on. So just be aware that there is a little bit of lag time. You're welcome to follow along, and you may just end up a little bit behind as cells run. One thing that's important to note is that you can only run one cell at a time. So one cell will be running, that will be taking up your GPU and taking over the process, and then you have to wait until the next cell is run. So just be aware of that. What it means is I'll be able to quickly demo things really quickly, but if you were to try to follow along, you might be caught a little behind. So I showed you how to run this first cell. So all this is saying is, if you're interested in the code side of this, this is actually a magic Colab thing to set us to using TensorFlow 1. StyleGAN is not available in TensorFlow 2, so we have to make sure that it's set to TensorFlow 1. And then this line is just showing us what GPU we have available to us. So I've run this a couple times now, but you'll just sort of see I'm still a V100. That won't ever change. The only way it changes is if it gets disconnected. So let's scroll down here a little bit to the next cell. So like I said, this is kind of Bash, but kind of also its own Python interpreter. So in this case, we're actually going to run some Python code, which is just going to define a couple of variables and a couple of functions for us. So you can play video directly inside of Colab. You can also display images directly inside of Colab. So these two lines of code do that for us. One note is the video thing is a little iffy. If you try to play too big of videos, it will sort of crash your RAM and force you to restart the machine. Everything that's in here should be small enough, but if you try to play along or add more frames to your videos, you may run into issues. So we'll see how this goes. Fingers crossed this works for us. And this last one just generates images. So we'll take a bunch of our images and create an image grid to make sure that we're generating lots of cool images. So anytime you have a cell like this, even though it's only defining variables and functions, you have to make sure you run it. So we're going to go ahead and hit Shift Return. That should be pretty quick. Next step is we want to install the StyleGAN2 repo. So this is just going to grab everything from Git and it's going to clone it into our Colab notebook over here. So I've already done this. I'm actually not going to run this cell because running this again would get pretty gnarly. You only want to run it once per session. So if your machine is on and running, you want to make sure you run this. So you would just come over here and hit play, and that would just install this code. It should take maybe a minute. It's pretty quick. We're going to use my fork of the NVIDIA repo. The reason we're going to use my fork is I've added a bunch of tools to allow us to generate videos very easily. NVIDIA only really allows you to generate images, and you kind of have to hack your way through it to get video out. So I've added some functions that make that a little bit easier for us. So once you have run this cell, you also just want to run this last cell here, which is just going to CD yourself into that folder. So I can actually, what I would do on my end, because I've already have run this, is just make sure that we're moving into that folder. So I'm in that folder. So what you should see over here is, if you ignore the network.pickle, for now, if you come over here, sometimes you have to refresh your file browser. So if you come over here and click on the file browser, and then click on the second icon here, which is refresh, you should now see a folder that says StyleGAN2-ADA, and that will be in your folder. So the next thing we're going to do is we want to download a model file. So if we were training our own model, that we would set up a data set and train it, and then we would generate a pickle or a model file ourselves. Because we only have an hour and a half in this class, I thought that what would be easier would just be to use a pre-trained model file. So we're actually going to use NVIDIA's Met Faces, which is a model trained on painted portraits from the Met. So if you click in here, and I can actually run this line and it'll just replace my image or my pickle file. If I run this cell, this will just download a file from this URL, and it's going to rename it network.pkl. That is a pickle file. These files hold the weights of our model, and we can then use that model to generate our images from it. So where can you find some of these? So NVIDIA has a number of models already pre-trained that you can access from their paper. There's also a really great GitHub repo run by one of my internet buddies, Justin Pinkney. He has a repo of a bunch of trained models that people have sent him. I sent them one of my abstract art pieces, but there's other models on here as well. Lots of faces, some cars, some anime, lots of anime actually, and some other things as well. So at the end of class, we'll actually look at maybe grabbing one of these and working with a brand new model. But for now, we're going to work with this NVIDIA Met Faces because it's a pretty nice model. I generally avoid teaching about faces because there's some ethical issues there, but because these are paintings of old dead people, I think we'll be okay. And it's just still really a really nice model. And I also think some of the stuff we'll be looking at is easier to understand with faces than it is to understand with some weird abstract piece. So we'll look at this. It's a pretty good model to work with. So make sure you've run this. It took me, I don't know, 5 seconds to download this. It was pretty fast. So make sure that you have your network.pickle file over here. You might need to hit refresh again. Okay, so now we basically have installed all the code. If you were to come back to this tomorrow or a week from now, just run every cell top to bottom, and you will sort of still get all the results we've gone through in this class. And as Mia mentioned, this will be recorded, so you can go ahead and watch the recording again to sort of remind yourself how it all works. I have added notes in most of these cases above each cell, so if you wanted to read through it, hopefully that would match sort of how I'm presenting it here. So we're now up to this cell here, which is, oops, this one down here. So we're ready to start generating images. You'll sometimes hear this referred to as inference, evaluation, or testing. This is taking a model and being able to generate images out of it. If this were a classifier model, it would be able to give a model, give the model a bunch of images, and it'd be able to classify that's a dog, it's a cat, that's a mouse, whatever. So we're going to generate some images. So one thing you can always do is you can always take the code from here, and you can always, so this is running the script. So we are now inside of this folder. And there's a handful of scripts here. There's one called generate, there's one called projector, which we'll be using, and there's one called style mixing, which we'll also briefly look at. So one thing that I always find helpful when you work with a brand new model is just to do Python and whatever the script is called, and then -- help. And if you run this, it puts out a bunch of text that basically says, here's how to use this thing. So in this case, we've got some arguments that we can pass in, commands, and then there's some examples here. Now, I haven't updated these examples with my latest stuff. It's probably something I'll do this week. But this is some examples of how to generate images with the, like, essentially this is what the Met Faces example is. We're actually going to run this. So it's always helpful to sort of like look at this and see what's being output. If you're ever stuck or don't know what you're doing, -- help is always something that can sort of obviously help you. So we're going to go ahead and jump in. We're going to generate some images. So the way this works is, again, we're going to pass that script in. So it'll be generate.py. We're going to pass in the subcommand of generate images. So inside of the script generate.py, there are multiple commands, and we'll look at a bunch of them today. But generate images is just a really straightforward one. It's just going to generate some images. And it's going to generate based on how many seeds we want, the number of images. So whenever you pass this script in, there's a couple of things you need to make sure that you pass in with it. So anything you see -- this is called an argument. So we're going to pass in an argument of the network. So what the network is it's looking for the pickle file. It's looking for what's the model that I need to be working with. So if you recall, we're going to use the network.pkl file. This is the Met Faces. If you're ever trying to change this path, a really simple thing is just to click on the file, to do right click or control click and hit copy path. And then you just come over here and you paste this in here. So that will paste in this model, and then we can work with this. So seeds. So seeds are essentially, if I go back to my slides over here, a seed is essentially a point in space. So what this does is this takes a random value and it generates a random value for this seed. So a seed is a single position in space. So seed 0 might be over here, seed 1 might be here, seed 2 might be here. So what we can do is we can say, I would like a number of seeds, and we can pass this in either as a single value. So we could say seed equals 0, or we could say seed equals 1. We could also pass in a comma separated list. So we could say I want seed 1, I want seed 10, I want seed 100. We can also pass in a range, which is what we're going to do here. So if you just do 0-25, this will say I want 26 seeds going from 0 to 25. If you're familiar with using random seeds in generative art or other things, essentially this is just generating a random seed of 512 dimensions from that. Another thing we want is we want the output directory. This is going to say where should I put these files? I'm going to put these in a folder called outdir, out. So that is going to end up in this folder here. If that folder doesn't exist, it'll just make it. So I believe Valentine asked, how are seeds converted to latent space coordinates? So this is using a thing in Python called random seed or I guess it's a NumPy actually. And it actually provides, I don't know the whole math behind random seeds. I believe it uses the computer's timing to basically figure out what a random seed value is. So you provide a random seed, and then when you ask for a random set of variables, depending on what that seed is, the seed will always provide the exact same number. So what's nice about this is seed 0 will always be the exact same image. Seed 1 will always be the exact same as seed 1. So whereas you might ask the computer for random values previously, you would get actually different random numbers each time. When you use a seed, you get the exact same numbers in the same order. So when we ask for seed 0, on every computer across the world in this model, you will get the exact same image, which is very nice and really helpful, as we'll see when we start to generate videos. Amila asked if we're going to learn to train models. We're not going to learn to train models because that takes a lot more time. I have some reference materials if you're interested in doing your own training that I will show at the end of this course. So keep an eye on that, and I will make sure that we show that. Yeah, so okay, so we're ready to set to run here. There's one other value that we could use, and that is this value --trunk, which we could look at. I'm going to skip it for now. And I'll get to this in just a minute about what truncation is. So if you are following along, go ahead and click in the cell and just hit Shift Return. And for some of you, this will take a little bit longer than me. There's some TensorFlow plugins that need to be installed and run. So this process, these two lines here, will take a little bit of time just to get set up and run. For me, this will be a little bit quicker because once these are set up, they are then cached into the system. So this runs pretty quickly. It's not real time, but it is pretty fast. And you'll see here, it's just generating each value. And so remember that you can't run another cell until this is finished, but you'll see that it has now finished. So we can now take a look at a couple of these. So I've written some code to quickly generate a grid of images that allow us to basically assign a series of images in this array. So if you wanted to look at, we can look at, let's look at image 25. Let's take a look at what we got here. So let's just we'll do seed 0, we'll do seed 1, let's do seed 10, and let's do seed 20. So this will give us 5 images back. So if you set up this list of image names and then you run this cell, this will basically show all of these below in the output. So we'll go ahead and run this cell. This also can sometimes take a little bit of time just because we're converting these to base 64. It's sort of a hack around displaying images inside of the Colab output. Cool. So now we see our, this is seed 0, this is seed 1, this is seed 10, this is seed 20, and this is seed 25. Now, if I were to run this tomorrow using the exact same seeds, I would see the exact same images. So just be aware that, like, you know, this is really the power of seeds, is that you can save these files down to your computer and then be like, oh, I want to manipulate seed 1 a little bit. And you can come back to the machine, come back to your notebook and edit it, which is really, really nice. And it's sort of what makes seeds really valuable. So I'm not going to download these images. If you wanted to download these images, you've got 2 options. One is you can download each one individually by right-clicking and hit download. That is a pretty laborious process. I don't necessarily recommend that for everyone. The other option is in Colab, because this is Bash, you can run a script to just zip out your, just convert your files into a zip folder. So if I turn this in, yes, if I just run this cell, this will take all of the images inside this folder, and it will generate a zip file called generate.out, and I could download this. There's also a way to mount Google Drive, which I won't cover in this class, but if you're interested, I have some materials on it. You can mount your Google Drive, and then you can drag folder files in and out as a way to get access to those. Okay, any questions about that before I move on to our next step? So we've generated some static images, and these will just be, we'll be using these to actually generate videos from. So this is pretty basic. You could take any model and you could generate a number of images. I should also add there's no limit to the number of seeds you can generate. You could put in number 1 million into this thing. Oh yeah, Amala asked, is the resolution of the generated image bounded by the model? It is, yes. That is a great point. So some models, if we look at this pre-trained model set here, you will notice that some of these are of a certain resolution. So this one is 512 by 512. Met faces happens to be 1024 by 1024. So the model is trained at a certain resolution, and you cannot deviate from those resolutions. There are other machine learning models that allow you to do super resolution, which makes an image larger with hit or miss results. But yes, that's a great point that each of these images is set to 1024 by 1024. I'm doing a thing here where I believe in the code, I'm able to set the size. This argument sets the size, so just so I can fit them all on the screen. But yes, that's a great point that all models are bounded by their size, and you are sort of beholden to that. Cool, so let's move on to looking at truncation. So I have some slides here about truncation. So this is an example of truncation. So truncation is essentially a way that we can mathematically determine how realistic an image is, or like the diversity of an image. Whoops. So I'm going to go ahead and play this video. So this is an example of FFHQ. And it starts, I believe, at 0. The truncation value is 0, and it goes up to +2. So you'll see when it's at 0, it's a fairly normal looking image. And the further it gets away from that truncation value, the weirder it gets. So just be aware that, like, if you go really high, you can technically go as high as you want, but anything past 2, you're going to get some really, really weird results. So how does this work? So essentially, with the name truncation, you could probably guess that, like, what this kind of does is it like actually truncates the space. So imagine that maybe in the middle of the region are all of your like realistic, good-looking images, and toward the bounds or the edges of this space they start to get weirder and odder and stranger. Now, this is sort of this is an analogy. It's not really how it works. If you're interested, the reality is like it sort of works in the sense that like it figures out the distribution of space, and then it finds sort of where the average distribution is, and truncation tries to move the space to match sort of like where the most average or the largest activations are in the space. So that's actually a little bit outside of my knowledge. I'm more of an artist and less of a mathematician. Other folks in here might have a better way of describing that, but it's sort of the idea is just that you're moving toward the space where the most realistic images are. Cool. So let's take a look at how to do that inside of our notebook. So there's a whole section here on truncation. What we're going to run is we're going to run a command that actually does what is called truncation traversal, which is essentially like taking a single seed and looking at all the truncation values available to that seed. There's two things you could do. One is that in actually generating the images, you could pass in a truncation value. So I believe the default, if you don't pass in anything, is 1. But if you pass in trunk equals 0.5, that will give you a truncation value of 0.5, which means pretty realistic images, but less diversity. So there's always a trade-off of the lower your number is, the more realistic the image looks, but also like the less diverse of images that are available to you. But what we're going to look at is we're going to look at actually just like taking a single seed. So we'll look at seed 1. Actually, let's look at seed 0 because we kind of know what that already looks like. So seed 0 is this image. So we're going to take this image and we're going to apply truncation to it in a series of steps. So we're going to start with -2. So truncation can be both negative or positive. Most people tend to go from +0 to about 2. We're going to go from -2 to 2, and you'll sort of see the difference on the negative and positive side. And we're going to increment it by 0.1. So that means we're going to start at -2. The next frame will be -1.9, and it'll be -1.8 up to 0, and it'll go 0, 0.1, 0.2, 0.3, and we're going to turn this into a video. So the code for this, if you just pass in truncation traversal and you pass in your seed, so there's only one seed applied to this, and then you pass in the start and the stop values, and then you'll pass in how many steps per frame of video, and then where it should go. And then we can also pass in a frames per second when it generates video. So this will both generate, I've already gone ahead and run this. You're more than welcome to run it now if you're interested in playing with it. I've gone ahead and run this. So this will generate a series of frames. This generates 40 frames, and then it generates a video. So at 30 frames per second, this is going to be a pretty fast video, but we'll scrub through it a little bit slower. It automatically generates a video. So for those of you who just want to produce videos, this is a really nice way to do it. If you're a little bit more of a control freak and want to maintain the value or like have a higher quality video, you also have access to all the frames as PNGs. So pretty nice setup there. When you run this code, it will literally start spitting out, sort of what frame it's generating, and then it will convert it to a video using FFmpeg. And then I've got another little nice little snippet here that will allow us to play this video directly in line. So what I've done is when this video is produced, I just sort of grab the path here, copy path, and then you can come in here and you can paste this path in. And then give a width and a height. So again, this model is 1024 by 1024. That's probably like a little big for my monitor. So I'm going to go ahead and set it to 512 by 512. So you can go ahead and press play, and this will happen really, really quickly. But you'll sort of see that at 0, you get an image, or sorry, at -2, you get an image that looks like this. At 0, you get an image that looks like this, which should be the thing to know about truncation of 0 is a truncation of 0 will always give you only one image and will always give you the exact same image. That's sort of known as like the most average image of that model. And then when you scrub up, you will get at this at positive 2. So Valentine asks, can you generate live streaming of these images? I have seen some people be able to generate live streamed versions of these. That's probably only happened really recently, and there's some complicated ways to do it. I don't generally do a lot of live streaming or like a live rendering or real time with StyleGAN. It's definitely not perfect, but I have seen some people with some other ways be able to make it work. But in these videos, you generally produce them sort of one-off. Okay, so that covers truncation. So again, remember that you can pass those in for standard images as well. So if I wanted a -1 truncation value for seed 1, it would probably be about here. So you can go ahead and pass it in images. Pretty much every other image or video generation that we're going to look at can also take in truncation. I might skip it just to save us a little bit of time, but you can change the truncation value of any of these models or any of these image and video generating systems. So we're at about halftime. So why don't we do this? Why don't we take a 4-minute break? I'm going to go grab some water so I don't lose my voice. So why don't we take a 4-minute break and then we'll come back at 22 after. So it's 6:22 for me here. So we'll just pause for a second. Let's go ahead and stand up, stretch a little bit, and we'll come back in 4 minutes. And if you have questions, feel free to drop them in the chat for me. All right, welcome back, everyone. So Valentine has a question of, is truncation 0 as close to the original as possible? He also added, are we in danger zone of reproducing the training data set at truncation equals 0? So truncation 0 doesn't really necessarily mean that it looks exactly like your data set. What I would describe it as is like it's the most average of all of the features that the images have. So truncation 0 will only ever return a single image, which means hopefully you've trained it on something larger than a data set of 1. So it probably won't be an image that's in your data set, but it will be something that is like the most average features that the model could find, if that makes sense. So let's go ahead and start to talk about interpolation. So we showed how to do a video using just truncation, but there's also a concept of interpolation. And interpolation works with the idea that, again, let's say that we have 2 images in our data set, or sorry, 2 images in our latent space. So we've got an image here which corresponds to this face. We've got an image here that corresponds to this face. So if we move very slowly from here to here, and at each one of these points, we take a frame or we take an image, what we have is an interpolation, right? So it animates from one face to the other just by moving along this single line to get to this space. And that's how we generate interpolations. It's as simple as that. So basically you take your 2 vectors and you slowly increment from point A to point B. Now, what's sort of interesting about StyleGAN is StyleGAN has 2 latent spaces, remember? So we talked about that mapping network, and that mapping network is referred to as W, whereas the basic latent space is referred to as Z. So Z is the train space. It's sort of regularized to make sure that all the space in this latent space has images in it, whereas the W is mapped, like it's mapped in a different way, and it's meant to represent hopefully a way that is less entangled. And I'll show you an example of what entangled means. So entanglement is essentially, here's an example of linear interpolation in space. So we're going from this face to this face. And what's interesting is, like, you'll notice that this person has no glasses, right? So when they go from this face to this face where there's also no glasses, we shouldn't really have glasses show up, right? So this is an example of entanglement where you're going from one, like a human readable image from with no glasses to no glasses, and yet somehow glasses pop up in this interpolation. You'll also notice that this person's mouth is closed and this person's mouth is closed, and yet somewhere in the middle we get the teeth showing. So this is a case of where we've got what we would call feature entanglement. The W space hopefully does not have that. So this is an example of the W space where you'll see the mouth never opens, it never gains eyes, but we will see that these 2 faces look pretty different, and so do these. And this is a case of where the W space is better for having smooth interpolations. That's one way of describing it. Like, maybe from an artistic perspective, we want a little bit of bounce and a little bit of noise. But from a theoretical and data science perspective, we want less noise and less entanglement. So let's look at 2 examples of how to generate these in Z space and in W space. So if you come over here, you will see that there is a line here for generate latent walk. So there's a couple different generate latent walks. So a latent walk is essentially a walk through latent space. And this takes in the pickle file. This takes in a walk type, which is a line Z. So you want to go in a straight line using the Z space. And then you pass in a series of seeds. So you could go just from like 0 to 2, and that would generate a single line from seed 0 to seed 2. In this case, what we want to do is we're actually going to do something a little different, which is we're going to go from seed 0 to seed 2, then to seed 5, and then back to 0. And what that's going to produce is going to produce a loop, right? So if you start and stop at the exact same seed, and you play it on a loop in like Instagram or something, it's going to generate a loop. So what this does is this will provide all of those frames. And if we look here, the outer is in Z-walk. So in here, this produced a number of frames, I believe 240 frames, and that produced a video. And this video looks like this. So that went from, we'll see here, seed 0, which is this image, to this image, which is also seed 0. And in the middle, it looks like we've got a curly-haired person, a person looking a different direction. So that's the interpolation in Z. Now, if we run the same thing in W, Sometimes you get subtle differences and it's not as clear as that example I showed you. But let's see what we get here. So I couldn't really see a huge difference there. I bet if I actually looked at these side by side, I might see some subtle differences. Sometimes it's subtle, sometimes it's very clear, but you get different things. So in general, these are two different spaces you can operate in. So line W or line Z, they're both different spaces. And again, you could play with truncation level here. There's also a setting here if you want a longer video. You can pass in a frames value. So I believe frames defaults to 240, and you can pass in, if you want to produce like a, I guess it would be like a minute long video, it would be this many frames. What I recommend playing with is like, if you have this many frames, you might also want to, add in some additional key points. So you might add in some additional seed values. Amela has a question of, is the latent space guaranteed to be smooth or on a well-trained model? Have you seen models where things blow up in the middle of the 2 points? Yes, I have seen that, and that is a great point. So definitely, like, latent spaces are not as smooth as you would think they are. The concept is that the W space is more smooth than the Z space, and it's hard to describe whether like something that has bouncy or is a little bit noisy is a poorly trained model, or it just means you don't have enough data, or if it just means like something else. So there's lots of examples where like the Z space will quickly transition, and that just might mean you've got a cluster of data that is like very narrow, and it's hard to sort of like figure out how to interpolate outside of that space. So it can be a challenge to sort of think about what a good looking model is, but this is definitely one way of figuring out what a good looking model looks like. In general, I would always recommend playing with the NVIDIA models and sort of like using them as an example, and then seeing what your own model looks like and seeing if they're like differed or like, how different they are. So there is one other version of interpolation that I want to show everyone, which is the idea of a noise loop. So this is actually, see if I have some code here. Yeah, so linear interpolation using the line type does sort of this. And one thing to note is that if you're going from like a very long, like if imagine these two places are very far apart, and we're going the same number of frames between those, that will feel like a faster movement, whereas something that's a little bit closer to each other will feel longer. So just be aware that like sometimes where you are in the space can determine how quick or how smooth the video feels. That's one of the challenges of using linear interpolation. We're going to look at another example, which is, oh, I don't have an example of it here. Oh, yes, I do. Okay, noise loop. So this is basically like, whereas the other one, you have more control about what your points are. Like you want to say, like, I want to take this image and this image and this image. The noise loop will give you sort of like a little bit more of a smoother video. But the challenge is like, you don't really get to control the points, right? So we're going to do like, we're just going to take like a long little walk through the video, and we're going to come back to the same place we are. So that is using this command. So instead of using walk type of line Z or line W, we're going to use noise loop. And we're going to have a start seed. This start seed doesn't really affect anything except sort of where this is kind of used to manage where you are, but it's just these are a little chaotic, I'll be honest. And then it also takes in a diameter. And the diameter is like, how wide of a space do you want to take in? And again, this is a little bit of an analogy more than it is sort of like an actual thing. Like there's no mathematic value that says like a diameter of 1 means the entire space, a diameter of 10 means something else. This is just a little bit more of like, do I want to take over a little loop in a long space or in a short space? So just think about it that way. And then, so RT asks, are seeds the same distance apart? So the speed of the animation between seeds 1, 2, different from 1 to 5? No. So this is a little bit of the funky part about seeds, is seeds are still random. They're assigned a point in space, but you don't know the exact distance from those. So if you wanted to get into like exact distances or like managing speeds, you'd actually want to manipulate on the vector level. So actually like in that 512 dimensions, you'd want to say, I want to go 0.25 to the left or to the right. I don't have a code to do that, but if people are interested in making that, I could probably figure out how to do that. But yeah, that's a bit of a challenge with this, is like, you don't really have that much control over these. And I should also say that the space, so this gets back to Amala's question, which is like, what is the space like? Like, are the spaces dense? Are they always smooth in these areas? And the truth is, even if you go from like the same distance, you might be moving through different features, and it might feel faster or move faster than other things. So one of the challenges with this work is like, I often talk to animation artists or the things, and they're like, I want to control like way more of this. How do I control more of this? And the challenge is like it's kind of hard. So this is one of the challenges with GANs today. I assume that like we will be getting through more of this, or like we'll be getting better tools for this in the near future. But for today, it's definitely still a bit of a challenge. So I'm going to go ahead and show what the noise loop looks like. I'll paste this in and I'll grab my noise loop code if I can find it. All right, while this renders out. So Valentine says, latent space seems to be the knobs that let you explore and control the output of the network. What are some best practices of navigating the latent space? Where can we explore it and find the interesting spots? So that is a really great question. I won't be covering too much of this in this session just because we have a short period of time, but you're essentially asking about feature vectors, which I do have a little bit about. Feature vectors are essentially the idea of like, I want to control just the space that puts glasses on people or not, right? Or I just want to control someone's hair color. So Photoshop recently released some new tools in their own model that sort of allows you to do that. Feature vectors is a huge topic and like something that I think we're going to see a lot more investigation in over the next couple of years, because now we've gotten to a place where like generating images is fairly good. Now people can focus on features and how to manage these spaces better. And the truth is there are some tools out there that are starting to get to that, but they're still very, very hard. Like it would be very hard for me on a custom model to figure out exactly what knobs to tweak to get an image to do this or an image to do that. Whereas with some of these larger scale like NVIDIA models, they've sort of spent more time to investigate them. So with things like faces, it's almost a solved problem, but it's still a little different. So this is a noise loop. You'll see that it feels different, right? It's like not as linear. It's sort of bouncing between different areas. And we've found a black and white space, which I didn't even know existed in this model. But this is kind of a fun thing to use just to sort of get a sense of the space and to like just sort of see all the various things in this. So if you crank up your diameter to say like 10 or 5 or something larger than 2, you will get a wider space and you'll see more images in that space. You can also play with how many frames you're using and other things to get a better sense of the space. So I like this just as like a fun little example. This is sort of what I'll usually, when I finish training a model, I'll throw this up on Instagram, just sort of show people what I'm working on, and people get excited about that. I'm actually going to skip style mixing. There's some slides in here about how to do style mixing. If you're interested in this, this is essentially the idea of taking an image in one position or in another position and like basically add faces together, right? So this is a great example of if I add a person with let's go back. If I add this face and this face, I should get some reasonable approximation that this is sort of the additive experience of these. The style mixing example here just takes in a set of seeds that are the rows and a set of seeds that are the columns, and then generates a grid that adds those together. So if you're interested in playing with that, you can play with this here. This line of code will work for you. It's pretty straightforward. I personally don't use this too much just because well, if I were doing it, I would just sort of generate my own vectors from these things by adding 2 vectors together. But that's there. I do want to look a little bit at projection. So projection is a really cool feature of StyleGAN. So let's talk a little bit about projection. So projection is the concept of taking an image that exists outside of your model, outside of your data set, and finding the closest approximation in your model. This should say model. So for example, what if I were to take someone who does not have a painted portrait in the Met, say Steve Jobs, or say another famous celebrity, and I were to put their face and try to find the closest approximation of their face in this model, how would I do that? So that's what we use projection for. And the way projection works is, again, let's say I have a picture of someone, in this case, Harrison Ford, and I want to sort of find where they are located in this latent space. So the first thing you do is you just randomly place them sort of in the middle of the model, and then you sort of doing some loss functions. You can sort of like at every iteration as it steps through things, it can sort of move closer and closer to where it needs to be in the model. And what that produces is produces a pretty cool video. This is an example. This is a very long running video. But as you see, it like slowly finds its way to the right space inside the model. This is a place where I find like the faces or Met faces or FHQ, which is the previous NVIDIA model that was really famous. This is where I find there's a lot of value in these. Like again, I don't really like working with faces. Again, sometimes find it kind of creepy, but this is a good example of where like something really makes sense to do this. You'll see this goes on for quite a while. But it sort of like never really finds Harrison Ford that well. And the reason for that is sort of a trick of this data set, which is that this data set expects eyes to be aligned like perfectly in order to find the nearest image of what you're looking for. So there's a challenge here of just sort of like you actually have to align the image in order to make it work. So what I've got here is some code that allows you to do this. So let's go up here. Let me see if this ran. It did not. Cool. So the way to do this is first thing you run the cell. This is going to make some new directories inside of your folder or inside of your repo. It's going to make one called align and one called uploads. And what we want to do is we're going to actually upload an image into this uploads folder. So the way to do that is just to go to your Finder. I'm just going to go to my desktop and I'm just going to grab this image and we're going to go drag it into uploads. And it's just going to upload our image into this file. Now this is going to take a little bit of time to work. So what I'll probably do is I'll probably move on and then we'll come back and sort of see what it does. Then you need to run this line of code, which is going to actually align your face to match the model as best as possible. So I'll run this. This might also take a little bit of time. So what I'm going to do is I'm going to go ahead and just queue up these lists here. Let's see what happened. Cool, that worked. So I had an image that looked like this. Oh, that's way too large. You can't even see it. And it aligned it to be a little, it's like actually tilted better. So it's a better aligned image for the data set. And then that gets passed into the projector. So I'm going to run this code. This will take a little bit of time to run. And while that happens, we'll talk about some other things that are available in this model because we're running a little short on time. I thought I could do this a little bit quicker, but apparently I can't. So we're going to run this and this will create the projection. So this is actually going to create this video. So it'll actually put these images side by side and be able to generate these next to each other. So go ahead and run this code. So that sort of concludes all of the basic things you can do inside of StyleGAN. I've got one other fun thing here, which is one of my friends built this sort of new script called what he calls flash digressions, obviously very into Cronenberg. And what this does is it actually messes with the base layers of the StyleGAN model. So the model is made of various layers. At the very bottom layer of a StyleGAN model is what's called the constant layer. And that is just a series of constant values. And those constant values tend to be pretty similar. Like we don't usually change those that much. And what this script does is it actually like changes those values a lot and actually does them in a circle. And what it sort of like causes the model to do is it like starts to try to hallucinate and like build things in places where it's not usually found. So you get this really cool effect of just like people being like sort of put up and everywhere and it's stretched and it's a little creepy, but it's like kind of fun too. So I've added this to my repo. You can go ahead and run this cell if you want to. So again, this just takes in a couple values. It takes in what pickle model you're using. In this case, PSI stands for truncation. So PSI is the same as truncation. And then it's how small of that constant layer do you want? And then what do you want the interpolation layer to be in a circle? So again, this produces a big video, but it's kind of fun. I definitely recommend like sort of checking it out. It's a fun way to play with things. So we're just at about the end of time before I want people to be able to play with the model a little bit and then ask me questions. I want to cover some like sort of next level examples of things you can do. So at the bottom of this cell here is just a bunch of links to other things. So I know at least one person asked about training, and my co-teacher for artificial images and I, her name is Leah. We actually just finished yesterday, Sunday, teaching a class on training in the brand new StyleGAN2 ADA model. So that is like brand new material, like we just finished it up. So those videos will probably be up on YouTube in the next few weeks. All of my classes go up on YouTube after we teach them, in part just because like I want to get that information out there for folks. So definitely recommend if you subscribe to my YouTube channel, you'll get lots more content just like this for free, or watch some ads to pay for it. If you are interested in jumping right into training training and you sort of understand how Colab works, we do have a Colab notebook that covers training. So you can go ahead and walk through that. Training in Colab is a little sketchy. It's not always the easiest thing, but if you also know how to convert Python commands in Colab to a server or your own GPU system, you can go ahead and take this and walk through that. There's also a demo video that I've already recorded on how to do that. So go ahead and follow that if you're interested. There are a ton of other like more advanced image and video generation techniques that I've added links to here. These links either go to notebooks or to video tutorials that I have. And then if you're interested, we do have some additional classes that are already up on our YouTube channel. So if you're interested in learning more about Colab, we have a 4-week class that's up on Colab. So it's like, I don't know, what is that? It ends up being about 6 hours of video on how to use Colab. Usually, if you want to do custom training of a StyleGAN model, you need to make your own data set. So we have a whole class on making your own data set. That's another 4-week class. And then lastly, there is a StyleGAN2 class we taught back in April that is also sort of teaching you how to think about all these StyleGAN models. And then the last 2 weeks are really about some of these more advanced techniques in video and image generation. So lots of resources here. You can also follow me. I have some links to myself, to like my website and other things. You can also follow me on YouTube or on any of my social channels, and you'll get access to a lot of this content as they roll out. I want to show some fun examples because I think it's like fun to sort of see what other people make. So one of the things that was sort of asked about is how do we better control these spaces? This is a thing called GAN space, which again is sort of the concept of how do we find feature vectors and how do we apply these in a way that like is almost coherent from a human level perspective. This is sort of, again, what Photoshop is started rolling out for faces. How do we make minor changes, how do we make major changes, those sort of things. This is a bit of a pain to use, but it is really cool when you get it up and running. Network bending is a tool from one of my friends that basically allows us to actually manipulate layers on sort of almost a Photoshop level. So this is an example of a StyleGAN model rotating in space, and it does really weird things when you rotate it because it doesn't necessarily know how to produce rotations the way that we might expect. So you get some really interesting videos and other really interesting ideas. There's a lot of stuff here that could be like played with way more than like most people have. Like the thing I would say about most StyleGAN materials is like someone will release a paper and they'll spend, a month playing with things, but you could spend a year playing with those things and find way more available to you there. So what's nice about the StyleGAN community is it is sort of growing, it's getting bigger, and there's a lot you can do with it. And like we're finding out new things we can do with it every day. Unlike network bending, there's also a thing called network blending. And maybe you've seen this recently. Justin Pinkney, who put up that StyleGAN2 pre-trained repo up on GitHub, has been playing a lot with this. The concept of this is pretty interesting. You're taking two StyleGAN models. So in this case, on the left, he's taking like a cartoon model. And then he's taking the lower levels of a cartoon model. The lower levels of a StyleGAN model are responsible for structure. So like geometric structure or just overall face structure. The higher levels are responsible for details. So what he's doing here is you can take in like an anime or another like sort of cartoon model, take the lower level structures of it, which gives you that sort of like, big eyes, like big nose, like, cartoon features. And you can apply the skin texture from FFHQ on top of it, which gives you this like almost Pixar 3D rendered looking image. And then what he's doing here is he's actually projecting in faces of famous people into those models. Similarly, on the right-hand side here is he's taken sort of a Japanese illustration style model and then applied the FFHQ facial textures on top of it. A little creepy in some ways, but also like kind of amazing that it's able to work like this. So Justin has a site called Tunify, which is really, really cool. It allows you to do this to yourself for any images that you want to upload. So I definitely recommend checking that out. Lastly, there is a recent paper that came out that is called Pixel to Style to Pixel. And what's cool about this one is it's using the StyleGAN network to actually do image translation. So someone here is able to draw things in Procreate, and those get rendered into the StyleGAN FFHQ model by taking these sort of shapes and figuring out how to render them. So really interesting stuff. There's a ton of development, I think, happening every day, especially with StyleGAN and GANs in particular. And I think we'll see more and more cool things available to us from here. So just like a very brief example of some really cool things that you can produce. But all this will be probably rolling out over the next couple of years, and we'll see way more stuff available to us. I've got videos and lectures and tutorials for a couple of these things. So if you're interested in seeing more of this, there are some notes here. I am sort of done with teaching classes for the rest of the year, so the next 2 months for me will probably be doing more tutorials around some of the content that I've started showing there at the end. So lots of really, really cool stuff that I think will be available to more people every day, which I'm really excited to sort of see what people make with it. Okay, so we've only got 10 minutes left. What I would recommend doing is, if you don't have any questions for me, go ahead and jump over to Justin's pre-trained model and try to download one of these. And then once you've downloaded one of the models, you can download it and drag it directly into your file browser here. Maybe try to run a couple of these cells and see if you get new images out of it. So I definitely recommend, maybe taking the next 10 minutes just to do that. And if you've got questions, I can answer them. And if you're not interested in this, but just have other questions for me, I'm happy to sort of take questions now. Yes, and Mia linked to Leah and my recent showcase as a part of Tumult Fest that we did last week with some of my students' works, showing some really cool examples of how to also use things like StyleGAN and Runway and other things. Let's see, I think our projector might be done. Cool, it looks like our projector is done. So why don't we go ahead and render this out? So if you're going to go ahead and just sort of play with this a little bit, I'm happy to stick around for the next 10 or 15 minutes and sort of answer any questions people have. And if not, I'll keep demoing some videos while we work. Let's see if this doesn't crash my Colab. Yep, all right, so that won't work. Let's just download that video. So sometimes you do get to a place of where trying to run these locally does crash Colab. You don't lose any work. One thing I should mention is I recommend downloading and saving anything you want to save. The sort of annoying part about Colab is when you do decide to get disconnected, and sometimes you get disconnected if you aren't working in Colab for about 15 or 20 minutes. When you get disconnected from Colab server, you will lose all your work. So it'll delete everything that's in your folder. So make sure that if you make a cool image and you want to share it with me or you want to share it with the community, save it to your desktop before doing so, before letting your machine crash, or I don't want to say crash, before letting your machine close, because you will lose that work. So I'm just going to download this video here. Why don't I also play what the flesh digressions video made? It actually might not have generated any video. Let's see. Yeah, it didn't. So I can run this. Cool. So I'm going to let this run. Yeah, so RT asks, can you explain the small and large radius and flesh digressions a bit more? It's a little bit of a challenge. So the small radius and the large radius, so the small radius is controlling the loop of that constant layer. So basically where things are sort of being positioned in the page is that's the small loop. The large loop is basically an interpolation of the top layers. So you can think about the large loop as being maybe almost like a Z length or a Z space interpolation. So I believe the default that ADAO set this to, I believe his defaults were something like 40 and 300. And I've sort of played with this a lot, and I just find if you just throw random values in, you get lots of fun, weird stuff. This whole thing is just sort of chaotic, and you also can't really control, if you're like, oh, I really like how this video works, how do I get back to it? It's a little hard right now. I'm probably going to add some additional features into it in the next couple weeks to make this a little bit more controllable, but it's still a little bit of a chaotic system. There is also, if we can actually one thing I want to mention is what's nice about Colab too is you can also look at the source code. So if you double click on a Python file, you can come over here and you can click on any .py file, and you can actually look at sort of what arguments are accepted into the model. So there's also something that I don't really expose to a lot of folks. There's also a step. So step 1 and step 2, and a video length. Video length, you pretty much never want to touch. I don't recommend touching this because it's set to 1.0, which means as you do a loop through that model, you want to do one continuous loop or one full loop. What you could play with is the step 1 or step 2 spacing. So I believe this creates a video that's probably something like 400 frames long. And this step 2 determines the length of this video. So if you make this shorter, like make this 0.01, that's the increment that it takes. This will produce a longer video instead of, like, I believe, what was it? It was 0.25. So that it's basically, it's whatever, 1.0 divided by 0.0025. So yeah, 400 frames. So one thing is you want to make sure that this is divisible by this. So if you were to set this to like 333, you would get a weird frame count, which means it won't loop. So make sure that whatever value you put in for that small step comes out correctly. And I believe this is set to 30 frames a second, maybe 24. So this will generate a video of 1,000 frames. So actually, let's see if this finished. It did. So I'm going to go ahead and grab this path. And I'm just going to paste this in here. And we can make our height and width a little bit smaller. And we'll run this. It's probably a long video, so it's just taking a little while to crunch and process. I would probably say for most folks, just downloading the video is easier than trying to run this show local MP4 video code, because this is converting all the video to base64, which just takes a while, and it can lead to RAM issues. So this is why I didn't do live demos of these things, because all this stuff takes a little bit longer. Yep, and it crashed, so it doesn't really work. So this is one I'll probably download and check out later. So we've got 5 minutes left. I'll stick around and ask more questions. One thing I want to note is if you're interested, you know, a little bit of just calling out some classes or things I offer. If you want to check out my website and you want to go to info about me, there is a newsletter sign up here. You can sign up for an email. We send those out maybe once a quarter, just with like what classes we'll be teaching in the future. And there's lots of other links here as well for me if you're interested in checking out more of my materials. So let's do this. Let's open up our projector and see what we did here. So if you recall, maybe 15 minutes ago, we started running this projection model, which basically allowed us to, we want to find this image inside of this model. So you can go ahead and do this. You'll see it kind of does this like wavy thing about like trying to find the space until it finally does. Not bad, not great. It's interesting. What I think is interesting is the lips kind of match here, but don't match on this side. Nose isn't perfect, but this is pretty interesting. Playing with projection is a lot of fun. There's different ways to do this. So Valentine asks, is there a way to merge 2 models together? There isn't. So that's sort of what network blending does. The network blending where you sort of take an anime model and a human model and sort of apply the skin texture of the model together. I don't know if there's another way you're thinking about it, but that's sort of the one way that lots of people are merging models together right now. All right, so we're almost at time here. So I just want to say thank you for coming by and checking out the session. If you have any feedback or any other additional questions, or if you have a cool image you want to present to me or share with me, this is my Instagram handle, so feel free to tag me on there if you make a cool image that you want to share with folks. And at DVSCH is my Twitter handle. So if you come up with something cool that you want to share or just have other questions, please feel free to drop me a line there. I hope everyone had fun. I hope you learned a little bit about StyleGAN, and we didn't move too quickly through the materials, or at least you have a notebook now to play with and watch afterwards. So, and as Mia mentioned, we will be recording the session. So if you want to come back and watch this and sort of like watch it slower or watch it faster, you can go ahead and do that. But yeah, I hope you had a lot of fun. I'm really excited to see what people make with this. And I hope that you check out some other videos if you're really interested in digging out into more. So yeah, thanks so much, everybody.
Thanks so much, Derek. That was great. As I mentioned, the video is going to be available on our page, and be sure to check out last week's session. That was also really cool with a lot of useful information and stuff that you could do. And I think that's about it for this session. Thank you so much, everyone. Getting lots of thank yous in the chat.
Yeah, thanks everybody. I hope you learned a lot. And again, thanks to the Twiml folks. It was a lot of fun.
Yeah, we had a lot of fun too. Thank you, Derek.
All right. Thanks everybody.
Bye, everyone.
Bye.